Good morning, everyone. Thank you, Ivan, for the introduction. Here I'm presenting our paper titled ADSB Reception Probability Modeling using OpenSky data. So just go quickly through the outline. First, we have the introduction here, and we will do some ADSB overview just to give some relevant context of ADSB and what's the relevant thing about ADSB on this paper. And next, we do reception probability formulation, methodology, results discussion, and we conclude the presentation. So for the introduction, as we all know here, ADSB was designed as an advancement of Mod AC and Mod S, and all of them use the 1090 megahertz frequency. And some paper discuss the potential use case of ADSB for self-separation purpose. So the idea was to move the separation management from the air traffic controller to the cockpit. But of course, we need a deeper understanding of ADSB before implementing this. And so far, we know that ADSB message reception is affected by distance and interference. Some paper already discussed this. And for the self-separation purpose, a model already exists these days, and this model has been used for air traffic simulations. And yeah, I mentioned some of the authors here. But we find some limitation of this model, that this model was only validated on a single interference condition. That is, it was done in early 2000, and then it was only done on one traffic and one airport condition. I will talk more about it later. So yeah, because we have more ADSB receiver this day, and we have a bunch of data, we want to validate this existing model and propose a new one. So how do we make ADSB reception model from open data? That's the main question. First, we discuss what is relevant from the ADSB. First of all, we know that ADSB is limited to line of sight. So if you fly very far from the receiver, then most likely if you fly under a certain altitude, you will not be detected by, or the transmitting aircraft will not be detected by this receiver. Also, if there is an obstacle or a terrain between you and the transmitting aircraft, here is the receiver, then most likely you will not receive the data. And this is an important thing in the reception probability modeling. And next is the receive power follows the freeze transmission model. So this model says that the receive power is inversely proportional to the distance squared. Then that affects the receive power, then the message reception itself, because the further you are, the less likely you will receive the message. Also, some paper from Strohmeyer and Sun here mentioned that there's interference from Mod AC, Mod S, and the Mod S extended squitter that affects the reception of ADSB message reception. Then we talk about the reception probability formulation, and I come up with this idea because I read this paper from 2017. This paper stated that the average update interval of position data increases with rising air traffic. Although this is kind of an insight, but we think that this is an imprecise measure of the ADSB performance, because position data itself, we know it is transmitted every 0.5 seconds. And when you say average update interval, it's kind of incorrect. So we formulate it in another way, and we call it reception probability. That is the probability of successfully receiving a message. And this probability itself, we assume it follows an independent Bernoulli trial, so it does not depend on the previous transmission. And the number of trials required before the first successful reception is given by this geometric distribution. And P here is the reception probability. And yeah, you can calculate basically for instance, you have a message and you can estimate where's the probability of this message is received by the first trial or second trial, and so on. And this is the formulation itself, and we have data from the 2017 paper. This is reconstructed data. We obtained the same graph, more or less. And what we can observe from this graph is we have bumps every 0.5 seconds multiplication. And because this is the position data, kind of obvious, the bump is related to the transmission frequency of the position data itself. And we have some spread here. So not exactly every 0.5 seconds, but rather there's also like 0.4, 0.3, 0.6, and so on. And this spread can be explained by the jitter in the transmission. So if you read the ADSB, some reference in ADSB, they said the transmission is not exactly every 0.5 seconds, but there's some tweak in there. Also, naturally occurring random jitter in the transmission and the reception itself, like the timing in the receiver also contributes to it. Then from this graph, the other paper stated in terms of average update interval, and we want to do it in the reception probability side. So how do we infer the reception probability? Then we do some analysis, and we see that if the jitter is removed, we stack them on top of each other, and we only have one bar every 0.5 seconds. Then the first bump represents the reception probability. And we can do the same by taking the area between 0.25 to 0.75 seconds. So we have the same time window there. And if you remember this equation, so the first bump is the P, because the I is 1. So the multiplication, the power becomes 0. Then the first bump is 0.53. Then if you multiply with 1 minus P, we get 0.249. And that's if you calculate the reception from the first bump. But if you, from the first bump. But if you calculate the area of the second bump itself, then the result is 0.233, which is kind of similar. So kind of this formulation is valid in this case. And yeah, that's how we come up with the reception probability concept. Next, this is the existing model. I will not dive deeper because the equation is quite lengthy, and I myself took some weeks to understand what is inside this. But the important thing is this has been used for air traffic management simulations, and also this model itself considers the distance in the equation and the overlap or the interference with mod AC and mod S. However, we found this limitation that data only validated on a single traffic and number of airport pair. So they validated only based on data from early 2000s or even earlier. And yeah, they did not validate it on another source of data. And also some constant in the model is based on specifications. So we find it kind of a bit loose how they calculate this constant, and that's why we also need to verify this existing model. And this is our proposed model, and this model is inspired by work from Kilat, and they developed this model for a vehicular ad hoc network for a car, and in their case, it was a good substitute for a low-level interference simulation, because this low-level simulation took a lot of time for them, and then they substituted with this equation. And we think that this model is transferable to our case, because in the model itself, they consider the distance and interference. So this is the distance, and the R max here is the maximum distance detected, and the D is the distance of the transmitter, between the transmitter and the receiver. And the interference itself is in the AI here. It is a constant that we will estimate later. So we talked about the reception probability formulation and the proposed model. Now we go to the methodology. First, we have position data, sensor coverage filtering, and so on. And I will talk deeply into this one. First, why position data? Because we know aircraft transmit different types of ADSB message. And we take the position because it's easy to filter out the noise in the data. For example, if there's duplicate in the database, then we can just remove the duplicate, because for position data, it's almost impossible to have a duplicate because aircraft is flying. And next, if you look at the position table in OpenSky, you will see that there's this timestamp from receivers and there's this global timestamp. And we take the timestamp from each receiver because there's another problem if you take the global timestamp, because each receiver has some variation in it. And I honestly don't know how this global timestamp is calculated. So because we focus on the reception of each receiver, we take the one from each receiver. And we collect data from year 2022 for this number of receiver registered in OpenSky data. And if you remember the equation, we have some maximum distance there. And that's kind of important. So imagine that you put a receiver and then next to you is a mountain or a hill, then you will have less distance on this side rather than the other side. So it's kind of imbalance in the maximum distance. So we filter out this kind of problem by checking if the coverage of the receivers is close to a circle. So we have the position data of the detected aircraft for this receiver, and we build a convex hull around it and calculate the metrics. And this metric basically says that if it is all of them are 1, then it's a perfect circle. But then we take these 3 values because we want to approximate like close to 1. And this is kind of an example of how it is calculated. Next thing is, after we focus only on the receiver with circular coverage, we know that the reception probability is estimated from the histogram. And it is quite impossible to take a continuous value of the distance and traffic, because we have to build histogram, and then continuous value means that you have to have many data. So we discretize the data into every distance and traffic bin. We take distance every 10 nautical mile and every 10 traffic. Also, because from previous paper, there is interference from mode AC and mode S. And we assume that the number of airports surrounding the receiver contributes to it. So we calculate the airport in sensor coverage. And again, problem in the data processing. So to build this kind of graph, you need to have sufficient number of data points. So we also check how many data we need to make a good prediction of the reception probability by doing this bootstrapping. And with that, we do this curve fitting. So we want to estimate the constant AI in this equation. And the AI, we assume it's a linear function of traffic and airport. Then we have the results. So for the result itself, on the left figure, yes, on your slide is the left figure. It's a scribble, looks like a scribble, but close to a circle. If you, the blue dot there is the center of the sensor, and then you can see like it's very close to a circle. And on the right figure, it's also another scribble, but you can see here, like the dot there, it's not in the center of every coverage there. So yeah, we successfully separate the circular coverage and the non-circular coverage here. And yeah, only 23 out of the more than 2,000 receivers pass this sensor coverage filtering. Then we take one distant traffic bin, and that has more than 100,000 data points, and we analyze the number of data points required, and we think that we select 2,500 data points as sufficient because the mean is kind of the same as when we have 10,000 data points, 4 times more, and the standard deviation is only 0.6%. So we think it's a good trade-off. Then when we take a look at one receiver, we analyze the effect of distance and traffic. Then it's visible here that the distance, like the more distance you have, the less reception probability we will get. And this is obviously follows the freeze transmission model. And when we talk about the traffic, the more traffic we have, the less reception probability also we will get. And next is the effect of airport. So for the other two, it was kind of obvious, but for the number of airports, we don't see any particular pattern here. What we would expect here is because we have more airports, then there are more interrogators on the to the aircraft, then we will have less reception probability. But from this graph here, we don't see that. Anyway, with this result, we continue to progress with the regression. And here is the result of the regression. So we apply the curve fitting for 22 receivers, and we got 11.8%. And we test the model on a totally different receiver, so different maximum distance and different number of airport, and we have 13.1% root mean squared error. So we use root mean squared error as the metric. And when we compare it with the existing model, the result is like 29.8%. So already with our model, we have a better metric or result compared to the existing one. And here is the regression result. So the orange one is the existing model, and the blue one is our proposed model here. And we have the comparison between the true reception probability and the estimated one from the regression. And what's interesting here is there is some constant offset on this direction, and we found that this is when the distance is more than 80 nautical miles, we have a higher RMSE than the average. And also here, when the distance is less than 50 nautical mile, this is like an outlier in the estimation, I think, because if I go back to one of the slides, we can see here there's a slight drop in when the distance is close to zero. And some paper has discussed this is the effect of donut effect. So you have less reception when it's very close to the receiver. And yeah, the rest, we have 8% root mean squared error here. And this is a histogram to compare how close we are to the true reception probability. Then for discussion, we successfully eliminate the non-circular coverage because it's kind of important for the reception probability modeling. Then we use 2,500 data for a single receiver. Effect of distance and traffic is obvious. And the effect of number of surrounding airport is not so obvious. And our existing model provide a better estimation of the reception probability. But we found that the estimation itself is not linear when we compare the estimated versus the true one. So maybe there is some unmodeled interaction between traffic and the number of airport because yeah, maybe it's not a direct correlation between the traffic itself and the number of airport and how they produce the interference. So we think that instead of number of airports, maybe it's better to have the mode AC and mode S in the equation directly. And yeah, this is the conclusion. So we think that with our proposed model, we already have a better estimation of the reception probability. However, there's always room for improvement, and we think that maybe the relation between traffic and airport or taking the mode AC and mode S into the equation is better. And yeah, for future works, maybe it's good to start from low-level simulation of the interference and yeah, take the mode AC and mode S into the equation. Also, maybe you can use some airborne ADS-B data to build the model. You can take this receiver on board and then fly with it and do some data logging there. I know one of us has done this thing, so maybe it will be good data to analyze also. And yeah, that's all for my presentation. Thank you.
Okay, thank you very much for this interesting talk. Maybe to warm up the questions, I'll start with one. I mean, I remember the paper from Martin 2014, I believe. Back then, he was my PhD student, and I was quite proud to have him. And he basically published a paper showing the probability of reception, but the paper also used the number of aircraft as an important factor that affects the reception probability. So have you considered that?
Yeah, I also considered that one, and actually we see some similarities there. So I think the paper talk on the percentage of message loss, and there is also a linear trend when we have increasing number of aircraft, and the percentage of message loss is also increasing.
Yeah, that's why, I mean, you somehow assume some stationary model which kind of does not change using the Bernoulli probability, where you kind of have a right? You don't basically have a memory of the state, right? So every attempt is basically independent.
Yes, and we look at it in terms of reception probability, not on the percentage of message loss. So kind of in a different point of view.
All right. Maybe there will be more questions related to that. I think Matthias was the first one. Microphone? All right.
Thank you. Thanks for the presentation. Quick question. I mean, you looked at data from different receivers, but did you also consider the type of receiver as a factor? Because that makes a huge difference. You can have one receiver at the same location that receives, like when traffic levels are high, say 800 messages per second, but you can have a different model that can degarble signals much better, and you can receive 3,000 messages. Like the differences can be huge, 3-time factor, for example.
Yeah, thank you. We haven't considered that one in this model yet, so I think it should be part of the future work. But indeed, I read one of the review, and we haven't considered that one, but maybe in the future work. Yeah, for the reviewed full paper, we should consider that one.
All right, thank you.
Thank you.
That was all the same, almost.
So again, thank you very much for your presentation. Just to add to the comment of Matthias, maybe also keep in mind that there are receivers with different sample rates, different gain settings, different antennas. And therefore, I believe that this should all be part of your model, right?
Yeah. For the different gain, I think it has something to do with the maximum range. So if you have more gain, of course, you will have more coverage. And because gain is related to the maximum range, I think it's already in the equation in the RMAX itself.
Thank you.
Any more questions?
Online question?
Oh, there is an online question. Excellent. Can we read it somewhere?
Sorry, that's there.
Online question.
Which range?
Maybe you can just read the question and answer.
Yes, so the question is, which ranges still give tolerable reception rate considering sending interval of 0.5 seconds? I mean, mean distance to receiver. Which range still give tolerable reception rate? I'm not really sure what do you mean by tolerable reception rate.
Maybe I find it also a bit confusing.
Yeah, like what is tolerable?
They will have to write in the chat because.
Yeah.
Like,
okay. Maybe we take this one offline.
Okay.
Right.
The Discord channel.
Yeah, sure.
Yeah, then you can. Okay.
Tolerable error rate. Well, I would say it depends on the use case of your. It depends per use case. For example, for an aircraft self-separation, I think. We don't really have number, but tolerable reception rate considering the distance.
You know, that's one of the situations when you say, let's take this question offline, and then you answer it.
I don't really have an exact answer. What is tolerable? Because it's kind of per case. You cannot have one value for all cases. For example, if you want to just have a good balance. You can use combination of receivers, and then you have a good reception rate. Yeah.
Maybe you can reiterate that the Discord link is at the top of the page.
So the Discord link is at the top of the web page on the OpenSky Symposium, and I think some of the questions will be answered then in the chat.